The next thing we are going to discuss is something called a constant volume gas thermometer. And based on this, how the Kelvin scale came into existence. Okay. And after that, we'll talk about thermal expansion as well. Fine. Now, consider a U-shaped tube like this. Now, if you pour liquid, okay, in one of the arms of the U-shaped tube or both arms also, okay, it doesn't matter whether you pour in one or both. If it is open on both sides, how is the liquid going to settle? It will settle in such a way that the height of liquid is same in both the arms. Okay, irrespective of area of cross section, it will settle in such a way that the height of liquid is same in both arms. Of the bottom branch, and the liquid will stop flowing from one side to the other side. It has to be like this. Okay. Uh, in the left arm, the liquid is open to atmosphere. In the right arm also, it is open to atmosphere. So the pressure here is P naught, atmospheric pressure. Okay. Now, one of you tell me what would happen if we increase the pressure on one side somehow. Okay. Maybe by keeping a piston or something. Okay, let's say there's a piston here. Or you add some extra weight on one side. Right? You apply a force here. What do you think will happen? Will the liquid level still be same on both sides or will it change? That is my question. Yeah. So if we apply additional force on one side, basically what you will be doing is at this point, okay, you'll be making the pressure greater than atmospheric, has to be atmospheric pressure. We had learned this in fluid mechanics. Okay. Now, if the pressure on the left side at that level is greater than atmospheric pressure, but on the right side it is equal to atmospheric pressure, then what happens? On the base, if you call this point as A and this point as B, obviously pressure at A will be greater than pressure at B. If pressure at A is greater than pressure at B, fluid will move from A to B. Okay. So liquid level on the left side will decrease and on the right side will increase. So if basically the pressure at A and B has to become balanced. Okay, the liquid will redistribute itself in that manner. Fine. So if you visualize that situation, when there is additional force acting on the left side, what happens is something like this. Left side, the liquid level will go down, and right side, it will rise up. Okay. Till when will this adjustment happen? Till the pressure at the same level in the bottom branch becomes equal. So due to this additional force that we applied, this side will come down, that side will go up. This is what is going to happen. Okay. Now, after the rearrangement of liquid, situation will be like pressure at A and pressure at B are equal. Okay. If pressure at A and B are same, then pressure at this point, okay, let's call it Px, and at the same level on the other side, pressure at this point, let's call it Py. These two will be equal. Okay. And see, by applying a force here, we are creating additional pressure on the left side. What is creating additional pressure on the right side to balance it? This extra liquid. Okay. So the additional pressure we created on the left side is balanced by pressure created by this liquid. Basically, it is rho g h. Okay. We had discussed all this in fluid statics. If this height is h, the pressure created by the force F on the left side is balanced by rho g h on the right side. Okay. Now, how did they make a thermometer out of this? It was found experimentally that the pressure of a gas, okay, varies linearly with temperature of the gas. Okay, when volume is constant. Okay, from the experiments that they conducted in olden days, They came to know this. Pressure varies linearly with temperature. Pressure varying linearly with temperature means what? If any quantity varies linearly with any other quantity, it means they have an equation between them, which is of this form. Y is equal to mx plus c. Okay, linear equation. Yesterday we discussed. Yesterday, what was the idea that we used in mercury thermometers? The length of the mercury column is proportional to change in temperature. Okay, that means length varies linearly with temperature. Now, they found out experimentally that pressure of a gas varies linearly with temperature. Okay. Next, pressure in a liquid column. Okay, it is expressed as P naught plus rho g h. Okay, if the liquid column is non-accelerated, this is how it is expressed. P naught plus rho g h. We had learned this in fluids. So from this equation, what can you say? Pressure varies linearly with height of the liquid column. Okay, pressure of liquid column varies linearly with height of liquid column. We can note that from this equation. Pressure of the liquid column varies linearly with height, because they have a straight line equation between them. The power of pressure is 1, the power of height is also 1, so it's a linear equation. Okay, they combined these two to make a constant volume gas thermometer. Now, where did gas come from in the picture? Let us see. Consider a U-shaped tube like this. Okay, this is how a constant volume gas thermometer is made basically. Fine. On one side, on the right side, let it be open to atmosphere. On the left side, let's say there is a bulb, closed chamber like this, connected to this tube. Just a moment, let me adjust this. Imagine an apparatus like this. Okay, there is a U-shaped tube which is open to atmosphere on one side. On the other side, it is connected to a closed chamber. Fine. If you pour liquid into this U-shaped tube, fine. Uh, let's say you start pouring liquid in the right side arm. It will spread itself in the lower side, lower branch. Okay. Now, when you start pouring additional liquid, what happens is on one side, it is open to atmosphere. Okay. So the pressure on the right side is always equal to atmospheric pressure. But left side, it's a closed chamber. Initially, the entire tube was open to atmosphere. So initially, the pressure here will also be atmospheric pressure. That's okay. But when you start pouring liquid, what happens? It will tend to rise. The liquid level tends to rise on both sides. Okay, on the right side it will rise. On the left side also it will have a tendency to rise like this. It will tend to be equal on both sides. But what is happening on the left side? Initially the pressure was atmospheric pressure. That's okay. But as you pour liquid, what is happening to the gas that is present there? It will effectively have to get compressed. Okay, just a moment. Yeah. You imagine gas being present in the left side chamber. Okay, let's say these are gas molecules. It could be air itself. It need not be any other gas, or it may be some other gas. It's up to you. You can imagine any gas. Okay. Situation was like this. The right side is exposed to air. Now, when water level or liquid level starts to rise on the left side, this gas that is present in this chamber up to here, okay, whatever gas is present, it will have to get compressed. Its volume will have to decrease. Now, if you compress a gas, what happens? Its pressure increases. Okay. So imagine that happening. Let's say the pressure of the gas is increasing here. As the volume decreases, as the gas gets compressed, its pressure increases. Okay. The molecules are forced to take or occupy a smaller amount of space. So effectively, its pressure increases. Now, if pressure is increasing on the left side, it becomes more than atmospheric pressure. Then if the pressure is more than atmospheric pressure, the liquid will not rise to the same height on the left side. There will be a small difference in height of liquid from left side to right side. This difference in height, you can call it as h. Okay. Now see, the pressure here where the liquid is open to atmosphere, is P naught. Then the pressure here at this level in the liquid will be P naught plus rho g h, where rho is density of the liquid, h is that small height. We know this from fluid statics. On the left side at the same level, what is present? The gas is present. It's not open to atmosphere. Okay. So the pressure here will be the pressure of the gas. And gas has the same pressure everywhere. Gas pressure won't vary significantly for small heights. Okay. This also we had discussed in fluids. So you can say that pressure of the gas is equal to atmospheric pressure plus rho gh. Okay. Therefore, what this equation effectively proves or shows is that pressure of the gas varies linearly with that height. Which height? Extra height on the in the other column. Okay. Now experimentally they already knew that pressure of a gas varies linearly with temperature. Okay. In Celsius degrees only. They didn't have the Kelvin scale back then. We are discussing how the Kelvin scale was invented. Okay. So in Celsius scale, on Celsius scale or Fahrenheit scale, if you take, it was found that pressure of a gas varies linearly with temperature. Now this shows that pressure varies linearly with that extra height also. Now if pressure varies linearly with temperature and pressure varies linearly with height, then we can conclude that from these two, we can conclude that pressure of the gas varies linearly. Linearly means the equation will be a straight line equation with extra height of the liquid. Okay. Now, basically what we want is a thermometer here. Wait, pressure varies linearly with extra height. This we already concluded. We don't have to repeat that. Pressure varies linearly with temperature and pressure varies linearly with height. That means temperature varies linearly with extra height. We can conclude that now. Okay, whose temperature? Temperature of the gas. Okay, therefore, temperature of gas varies linearly with extra height. Okay, now where did constant volume come into the picture? We never talked about volume being constant. I talked about gas being compressed here. Okay, see, based on the pressure of the gas, there will be a difference in height, right? Now, if you raise the temperature of the gas, you increase the temperature. Basically, when you heat anything, okay, especially a gas, it tends to expand. When you raise the temperature, the gas will tend to expand. Left side will tend to go down, right side will tend to rise up due to the expansion of gas. But if you pour extra liquid on the right side, okay, if you pour extra liquid, then you can prevent the expansion of the gas. If you raise temperature, gas will tend to expand. But by applying extra force, you can keep it compressed. You can keep the volume constant. Now, how do you apply extra force? By pouring more liquid on the right side. Okay. So based on this temperature, based on the temperature of the gas, you will have to adjust the height of the liquid on the right side to keep the volume constant. Okay. Volume of the gas, this volume that is there, we keep it constant. Fine. So obviously, as you raise temperature, the pressure of the gas will increase. Now, if the pressure of the gas is increasing, then the pressure of liquid on the other side has to increase. For that, you will have to increase this height. So if when temperature rises, pressure rises. When pressure rises, to keep the volume constant, you will have to raise the height. That is how temperature gets related to height. Okay. So temperature of the gas varies linearly with that extra height of the liquid in the right side column. Now, if anything varies linearly, no, the graph will be a straight line. That is what we mean by linear variation. Okay. The equation will be like this. Temperature is equal to some constant multiplied with extra height plus some other constant. It's like y is equal to mx plus c. Okay. Where y is temperature, x is height. They vary linearly with each other. Now, for such an equation, if you draw a graph, the graph will be a straight line. So what they did was they plotted graphs. Fine. Just a moment. Let me draw the graph. Okay. Now, they knew that temperature varies linearly with height, pressure varies linearly with height, temperature and pressure are also linearly related. So what they did was they plotted pressure on the y-axis, temperature in degree C itself. Okay, that is the scale they knew in those days. Okay, they took that on the x-axis. Now, when temperature is zero, also zero on the Celsius scale, that's basically melting point of ice. 0 degree C is practically possible. We observe that in daily life also. In fact, negative temperatures in Celsius scale are also quite common. Okay, in daily life. So even when the temperature is 0 degrees C, there was found to be some pressure in the gas. There will be pressure in the gas. Okay, so the graph starts from here. Let's say this is gas 1. When one kind of gas was used in that chamber and a graph was plotted, they got something like this. They got a graph somewhat like this. Okay, pressure varies linearly with temperature. They knew that when volume is constant, this happens. Then they repeated the experiment with a different gas. Okay, they may have changed the gas, they may have changed the amount of gas also. Okay, so number of moles could be changed, the gas itself could be changed. Now, if you change the gas, a different gas at the same temperature can exert a different pressure. Let's say this is gas 2. Okay, they again plotted the graph. Graph of what? Graph of pressure variation with temperature. They obtained a graph somewhat like this. It's a linear graph. They knew that. Okay, experimentally it was known. Fine. So they did this for many kinds of gases, different amounts of gases also in that chamber. Okay, sometimes one time they could have fit 5 moles of gas in that chamber. Another time they could have fit 4 moles of gas in that chamber. So different variations they tried. Okay, they got graphs like this. What they did was, see, in those days, as I said, on the Celsius scale, 0 degree C is the starting temperature. It extends up to 100. Negative temperatures also could have been known, but thermometer started from 0. Okay, so they started plotting the graph from 0. They got linear graphs like this. Now, after getting the graph, what they did was, mathematically, they just extrapolated the graph in the backward direction. Extrapolating means extending. Okay, theoretically extending. So what they did was they just continued the graph. They just extended the graph in the backward direction. If they did that, what they found was the graph cuts the x-axis at this point for the first gas. Okay, do the same for the next gas or a different amount of the gas. Extend it in the backward direction. They found that all the graphs were cutting the x-axis at the same point when extended in the backward direction. Okay. Graph cutting x-axis means what? Y coordinate becoming 0. What is on the y-axis? Pressure. Okay. So at this particular point, pressure of the gas becomes 0. And mathematically, this temperature was determined as minus 273.15 degrees C. So when the pressure temperature graphs of different gases were extended in the backward direction, the pressures were found to become 0 at this temperature for any kind of gas. Fine. So what do we conclude from this? See, gas exerts pressure due to random movement of gas molecules. Okay, liquid exerts pressure due to its weight. That is okay. But the weight of a gas is not that significant. You take a small amount of air, okay, in a chamber, its weight will not be that significant, but its pressure is significant. Okay, gas exerts pressure due to random motion of its molecules. You can imagine something like this. Let's say there is a bulb, like a chamber itself. You visualize gas molecules in it. The molecules will be moving around randomly and they'll be hitting the walls of the chamber. Okay, that is how they create pressure in the chamber. Fine. Now pressure of the gas is becoming zero. Can any of you tell me what this means? I am telling you that gas exerts pressure by means of random motion of gas molecules. So gas molecules will be moving randomly, so they hit the walls of the container. That's how they create pressure. What does gas pressure becoming zero mean? Fine. Sohan has given the answer that motion of molecules stops. Vanilla has given the answer that speed of gas molecules decreases. Okay. See, the motion of gas molecules stops is the correct answer. Good. Basically, pressure is becoming zero, no? That means they are not moving around anymore. They are not hitting the walls of the container. Means they are not moving at all. Fine. It decreases to zero all the way. That is when pressure of the gas becomes zero. So this is what is interesting. There is a temperature at which the pressure of the gas becomes zero. That means at a temperature of minus 273.15 degrees C, okay, movement or motion of gas molecules ceases or stops. Okay, this is what gave rise to the Kelvin scale. So scientists concluded that this temperature must be something special. At this temperature, molecules cannot move at all. Okay, so what they did was they called this temperature as the absolute zero of temperature. See, Celsius, when he invented the Celsius scale, he called melting point of ice as 0 degrees Celsius. That was a commonly known reference. So he used that as the reference and he said that let's take this as 0 on my scale. Fahrenheit took that as 32. Fahrenheit scale 0 is something else. Okay, some random value. Some other temperature scale could have used some other reference temperature as 0. But all the experiments show that at this temperature, on the Celsius scale, minus 273.15, at that temperature, pressure of a gas is becoming zero. So there is actually something special happening there. Okay, movement of molecules ceases. If gas temperature is, if gas pressure is becoming zero, gas molecules are not moving. That means liquid solid molecules also won't be moving. Okay, so there is a special temperature at which molecular motion stops. They decided, let's call this as zero from now onwards. Okay, that is what gave rise to the Kelvin scale of temperature. So on Kelvin scale, zero, okay, 0 Kelvin is basically this temperature, minus 273.15 degrees Celsius. Fine. So if you consider temperatures on the Kelvin and Celsius scale, let's say on the upper side, you have degree Celsius, lower side you have Kelvin. Then minus 273.15 degrees. We usually approximate it to 273 itself. Okay, that's fine. Exact value is minus 273.15. That much on the Celsius scale is 0 on the Kelvin scale. Okay. Next, minus 272.15. Okay, minus 273 to minus 272 is a change of 1 unit on the Celsius scale. Change of 1 unit on Celsius scale is the same as change of 1 unit on the Kelvin scale. So this is taken as 1 on the Kelvin scale. Next, minus 271.15 on the Celsius scale is taken as 2 on the Kelvin scale, and so on. You extrapolate that. Okay. If you come all the way to 0 on the Celsius scale, that will be plus 273.15 on the Kelvin scale. 1 on the Celsius scale will be 274.15 on the Celsius scale. Sorry, on the 1 on the Celsius scale will be 274.15 on the Kelvin scale, and so on. So basically what you can say is temperature in Kelvin is equal to temperature in degree Celsius plus 273.15. We approximate this to 273. Okay, usually while solving problems, we take it as 273. This is how Kelvin and Celsius scales are related. Remember, the starting value on the Celsius scale and Kelvin scale are different, but the unit sizes are the same. 1 unit on the Celsius scale is same as 1 unit on the Kelvin scale. Okay, therefore, 1 unit change of temperature in Celsius degrees is equal to 1 unit change of temperature in Kelvin scale. Okay, keep this point in mind. The starting value is different, but the unit sizes are same. So this is how you convert from one to the other. We could directly write this equation. Temperature in Kelvin is temperature in degrees C plus 273.15. Okay, let's go back to constant volume gas thermometer. So basically what it does is, by keeping the gas volume constant, uh, it relates temperature to height of the liquid column. Now, experimentally, it was known that temperature varies linearly with pressure of gas. Okay. And here we can relate pressure of gas to height of liquid column on the right side. Okay. Extra height of liquid column. So we proved that pressure of gas varies linearly with height. So combining these two, temperature varies with pressure linearly, pressure varies with height linearly. So temperature varies linearly with extra height. Okay. That is what we concluded here. If temperature varies linearly with extra height, then you can write a linear equation between them. Okay, like what we did yesterday. Yesterday in mercury thermometers, we wrote a linear equation between temperature and length of the mercury column. Here we can write a relation between or an equation between temperature and extra height of liquid column. Okay, how? T minus T1 divided by T2 minus T1 is equal to height of liquid column H minus H1 divided by H2 minus H1. So if you know H1 T1, height of liquid column at one temperature, and H2 T2, height of liquid column at another temperature, then you can tell temperature at any other height. Okay, so basically this is the working formula of a constant volume gas thermometer. Right? Nothing new about this. It is very similar to the equations that we wrote yesterday. Right. So basically, what is the summary of all this? Constant volume gas thermometer works on the principle that at constant volume, okay, pressure of a gas varies linearly with temperature when volume is kept constant. Okay, they knew that experimentally, and they related to height of the liquid column. So you can find out the temperature of the gas based on the height of the liquid column. And then they plotted graphs of pressure versus temperature for different gases, and they found that when extrapolated, all the graphs meet at the same point on the x-axis. Means whatever be the type of gas, whatever be the volume of gas, the pressure becomes zero when temperature is minus 273.15. Pressure of gas becoming zero means what? Molecular motion ceasing. So at that temperature, nothing moves. So they called that as the absolute zero of temperature. And then came into existence the Kelvin scale. Okay, let's solve one problem. You know how to convert from Celsius to Fahrenheit. You know how to relate Kelvin and Celsius temperatures. So what I want you to do now is 0 Kelvin. Okay, how much is, uh, fine, let's take 0 Kelvin itself. How much is 0 Kelvin on the Fahrenheit scale? Okay, don't use 273.15. Take it as 273 itself in the conversion and do this. Solve it quickly, all of you. Okay, I got three answers around minus 459 degree Fahrenheit. Okay, see in Fahrenheit, you are supposed to, like when you express temperatures in Fahrenheit or Celsius, you have to say degree Celsius, degree Fahrenheit. In Kelvin, you don't have to use that. Okay, you directly say Kelvin. Okay, now 0 Kelvin basically is minus 273 degree Celsius. Okay. So on Celsius, the temperature is Celsius scale, the temperature is minus 273. You have to convert it to Fahrenheit. Now we know that C is equal to, or C by 100 is F minus 32 by 100. C by 5 is equal to F minus 32 divided by 9. That's all. You substitute minus 273 here, you will get the corresponding Fahrenheit temperature. Okay. And okay, I'll take your answer to be correct. So temperature in Fahrenheit you are saying is minus 459, close to this degree Fahrenheit. Fine. So this is equal to 0 Kelvin. And yesterday we learned how to convert from Celsius scale to any other new scale also. Okay. Similarly, you can convert Fahrenheit to any other new scale. That means you can now convert Kelvin to any new scale. Okay. No big deal. Fine. So that is the first part of this chapter. Basically, what is heat, what is temperature, how is temperature measured, what are the different types of thermometers. Okay.